Hello everyone. Miss Monica, can you please mute yourself?
Hi sir, I'm Maunika from
Okay,
JNTU Pulvendula.
okay, thank you. But you can mute the audio. If you have no question at the beginning, you can mute. There's one option. Okay, okay, let me do it myself. Okay, it's fine. Since it's already 3-4 and some people have joined this session, let us start our ninth live session on the Semiconductor Devices and Circuits. This course is being taught by Professor Sanjeev Samadhan. So basically we are two TAs for the course who solve some of the problems related to the assignments and related to the concepts that are being built during the lecture hours by the professor. So today we will proceed on the MOSCAP further. So let me turn off the video and let us move further in the session, further forward in this session. So let's move towards the problems. Okay, uh, this third problem we had done, but we will be requiring this graph rather, for one of the problems. So I have kept it as it is. Now, wait a second. Krishna wants to. Okay, so basically, we are given a MOS cap which is same as in question 4, and we have been told to find the maximum depletion width. Question 4 we solved it previously in the previous what I can say, in the previous assignment. We solved up to question 4, and in question 4 we were given something about this substrate of this MOS cap. We were told that this MOS cap is having p-type substrate and the temperature is 300 Kelvin. The doping concentration was 10 to the power of 16. Okay, the oxide thickness is approximately equal to 55 nanometers, and the device area was given, and we were also given this intrinsic carrier concentration. Now building on this, we are required to find the depletion width, which is the maximum depletion width. So since we know this is a p-type silicon substrate, and we are applying some bias to it, as a result of which we are transitioning from the accumulation region to the depletion region and then to the inversion. So that we had seen these things in previously in this curve, this CV curve, how this was the accumulation region and how this was associated with this depletion region, and this point over here is the threshold voltage. This CV curve gave us lot of information, and this region was the inversion region, and depending upon the frequency of this AC signal that we were imposing upon this DC bias, we were able to find two or three conditions, rather I would say. One was this low frequency and high frequency on the AC signal, and another was the deep depletion, which was due to the fast ramping of this DC bias, as a result of which we didn't give inversion charge enough time to generate itself. So as a result of this thing, we were having this depletion region increase. There was the increase in the depletion width in order to accommodate or in order to encounter the charge balance that was being uh, uh, done by from our side. And we were, since we were applying large ramp on as on this, what I can say, on this gate, so this resulted in the large uh, change in the width of this depletion region. I shouldn't say large. This resulted in the increase in the maximum depletion width, because we were required to have this charge balance between the gate and the semiconductor. So as a result of that thing, we were having this increase in the depletion width in order to encounter for the charge balance that was being done from our side. So in this problem, since this is given that we have to find just the maximum depletion width. There is no condition about whether it is this fast sweep or slow sweep. So it is simply the maximum depletion width we are required to find, which is denoted by xt. So this solution for this is simply 2 times. We know this by solving this Poisson equation. You must have seen how you arrived at this, how you find out the electric field, then from that you find out the surface potential. Professor has taught it beautifully to us. So we pin this surface potential at 2 phi f. Okay, we say that the surface potential is pinned now at 2 phi f at the time of maximum depletion width. So this is the maximum depletion width for us. Okay, now for this phi f, it is simply given by Vt ln of Na by Ni. Okay, since this was doped up to the concentration of 10 to the power of 16, it is simply 25.9 milli, which is 10 to the power of minus 3 ln of 10 to the power of 16, and Ni was 1.5 into 10 to the power of 10. So this is the phi f. This is the value of phi f for us. So let's basically calculate this thing. So let's calculate this thing. It would simply be 10 divided by 1.5, which is the 6.66 ln of 6.66 into 10 to the power of 5, I guess. Yes, into 25.9. So it comes out to be equal to, phi f comes out to be equal to 0.347 volts. So this is the value of the phi f. Now let's put it in the equation for this maximum depletion width. Let me write it explicitly, the max. So it would simply be now this will simply be xt max would simply be 2 times epsilon s. Epsilon s is 11.7. Since this whole process of depletion is going on inside the semiconductor, which is silicon, and for silicon we have this relative permittivity to be equal to 11.7. So it would be 11.7 into 8.85 into 10 to the power of minus 14 since I am dealing in centimeters. Okay, that's why. Otherwise, epsilon naught is 8.85 into 10 raised to the power of minus 12 when we are talking about the units of meter. Okay, into this phi f. Phi f came out to be equal to 0.347. So it's 2 phi f basically. So it's 2 times 0.347 divided by Q is simply the electronic charge, which is 1.6 into 10 raised to the power minus 19, and Na was 10 to the power of 16. Okay, basically let us solve this. It shouldn't be that much. It's 2 into 11.7 into 8.85 into 2 into 0.347 divided by 1.6, which is 89.82 root of 89.82, which is 8.92 into 10 to the power of minus 10. Okay, minus 3. It is okay, 10 to the power of. Let me check once again whether I am saying it correctly or not. It is minus 3. It will be minus 7, and then it will be minus. So it is approximately equal to this thing. So this xd max will come out to be equal to, let me take this approximately equal to root of 3. So it will be 3 into 10 to the power of minus 7 meter, or it will be simply 0.3 micrometer. Okay, so it would be simply 0.3 micrometer. So basically let us check the options. So option D is matching our options, so we will select this option D. Okay, now let's move towards sixth problem. It says that we have the same MOS cap which was in question 4, and we have been given to find the effective capacitance which corresponds to the maximum depletion rate. So at this simply says that we have to find the total capacitance. So at maximum depletion width, capacitance will simply be this. This will be the series combination. Okay, series combination of the oxide capacitance and the depletion capacitance. So it would be simply 1 by Cf will be 1 by Cox plus 1 by C depletion. Okay, so it would simply be C effective will simply be Cox C dep divided by Cox plus C dep. Okay, this is simple. Now the C depletion would simply be equal to epsilon s by xd maximum that we found out previously. Okay, so this simply boils down. Okay, this simply boils down to the previous problem where we found out this value for this xt. We will put that xt over here, put that over xt over here, and cox we know we have found out in the previous what I can say previous case. In the previous problem it was approximately equal to, let me check the value of the cox that we had previously found out. It was, this cox was equal to 126 picofarad. Okay, so we need to just put these values in order to obtain the value for this capacitance. So let us leave this problem as it is. Okay, because it's just mathematical problem after this. Now let's move towards this seventh problem. Basically this is interesting problem for us. Now this is some conceptual problem rather, I would say. So it says that we have to consider this CV curve which is in question 3. Okay, this problem is in question 3. Okay, now in this problem we are required to find uh, comment about the two statements. One statement is that the MOS capacitor has n-type substrate for this question 3, or if positive voltages are introduced in the oxide, CV plot will shift to the left. So let me ask you people about this. So if you look at this curve, just by looking at it, what do you infer from it? Just I need some random guesses about this. Just if you think that you are incorrect, there is no harm in just answering this question. So what do you feel? Is this p-type substrate or is this n-type substrate for the silicon? If you consider the CV curve, what do you feel? Should it be n-type substrate or should it be p-type substrate? If you are considering the MOS cap, which is having CV curve like this, like this. So any comments? Okay, I guess we have no comments. So basically, if we consider this to be n-type simply, okay, if we consider this to be n-type substrate, it means that the accumulation should have occurred for the positive bias, as we have done it previously in the previous session when we were dealing with this n-type substrate. We did it vastly, okay, we did it very vastly when we are dealing with this n-type substrate. Let me check where we did this. This was for n-type substrate. Yes, here when we did for this n-type substrate, we said that the majority, when this Vg is greater than 0, this Vg is greater than 0, so it would mean that I will be accumulating, what I would be accumulating? I would be accumulating holes, okay? I would be accumulating holes. Is I am right? No, I am wrong. You must be aware what I am trying to say. You should have said that, sir, I think you are wrong in saying this, because whenever I am applying positive bias for the n-type substrate, it means that I am accumulating electrons, which is correct statement about this, because when I give positive bias to the gate and the substrate is n-type itself, it will attract the positive charges, will repel the positive what we can say charges in the at the interface of the semiconductor. So as a result of which there will be build up or the accumulation of the electrons at the interface. So it means that for the n-type substrate, if I am applying positive bias, large positive bias, it means that I will be accumulating electrons. But if we consider this figure over here, if we consider this figure, if I am applying the large positive bias, the this semiconductor MOS cap, it appears to be in inversion, and that too with high frequency. Clearly, this is the high frequency response, high frequency response of MOS cap, high frequency response. So clearly, this is not the n-type substrate, because when I am applying negative bias, I am having accumulation region. Okay, it means that when I am applying negative bias, I am accumulating holes at the interface, which is the correct thing for the p-type substrate. So just by looking at this accumulation region or just by looking at this depletion region, we can comment about this substrate. So as we have written over here, depletion region will not be formed if the MOS capacitor has n-type substrate. But from the CV characteristics, this C reduces if V is increased. So depletion region is formed. This is one thing or one kind of a what we can say procedure to look into it if we are considering the high frequency. Had it been the low frequency curve, we might have got it like this. Okay, we might have got it like this. So it might have been problematic for us to differentiate between the accumulation over here and the accumulation over here, whether this is the accumulation or whether this is the accumulation. This might have created confusion to us. But since we are looking into the depletion region, and depletion will only occur whenever for this p-type substrate we are applying the positive bias. So by applying positive bias, we are trying to deplete the region which is at the interface of the silicon dioxide and the silicon. Basically, we are repelling the positive charges and we are trying to attract the electrons to the interface. So we are depleting this region at the silicon dioxide and silicon interface. So this is what it says. Now it says that if positive charges are introduced in the oxide, because till now we had assumed that there are no charges in the oxide. So now if we are considering that we have charges in the oxide, what would happen to this p-type what we can say this p-type substrate which we are having in this case. So now if I am having positive oxide charges and I am having this positive what we can say positive oxide charges which are lying inside this oxide, as a result of this thing there will be attraction of the electrons to the interface and the holes will be repelled from the interface. So if I simply draw this what I can say this MOSFET, let me draw the energy band diagram so that we all get this thing, this image cleared. So if this is the metal side, okay, this is the metal Fermi and this is the oxide, okay, and this oxide is having positive charges at the interface like this. Okay, this is the oxide charges, okay, with some thickness, let's consider it to be T-ox, okay, and there is no band, this Fermi need to be aligned. So as a result of this thing, this is the Fermi level on the semiconductor side. Since I have this p-type substrate, this is the this will be closer to the what I can say closer to the valence band, since the substrate is p-type. Okay, so let me draw it like this. Because the substrate is p-type, it would be closer to the Fermi level. The valence band will be closer to the Fermi level in the bulk. Okay, this is the bulk of the semiconductor. This is the bulk of semiconductor. Okay, this means that since it is p-type substrate, the Fermi will be closer to the Fermi will be closer to the valence band edge. Okay, now since the positive charges are there in the oxide, this means that at the interface we will be having more electrons. So it means that the interface will be having bending like this. Okay, interface will be having bending like this. If this is the EI, this is the intrinsic Fermi level. Okay, it means that simply it is like this. It means that the surface, this surface is having more concentration of electrons. Okay, this is simple because we have this positive charge in the oxide. It would attract more and more electrons towards the interface. So the band bending at the interface will be, the bands will be, this Fermi level will be closer to the not closer, it would be closer in terms of the bulk conduction band difference. So it would be, the bands would be bent such that the, you can say, the conduction band is closer to the Fermi level at the interface as compared to the conduction band in the bulk, because in the bulk there is much more distance between this EC and EF, and in near this interface, because we have more electrons, so the difference has decreased. Okay, this simply means that we have been able to attract more electrons. Okay, this is the direction of the field in the semiconductor. Let us be aware of this thing. Since we have this band bending in this conduction band or the valence band, this results in the electric field, and the direction of the electric field is always upwards. It always points upwards the hill. This is, if we consider this to be the hill, the electric field is in this direction. Okay, let us be aware of this thing. Now, since I have applied this positive charge, this resulted in the resulted in the depletion of the holes and resulted in the increase in the concentration of electrons. Surface is having, rather than writing more, increasing concentration of electrons, it would be more correct in this regard. So it means that now, since I have positive charges in the oxide, I will be requiring now less amount of gate voltage in order to deplete my carriers, deplete the holes at the interface, because this work has already been done by the positive charges which are lying in the oxide. So this is the statement we have written over here, that if positive charges are introduced in the oxide layer, then to equalize the effect, applied voltage V must be reduced, because for the same bias there will be now inversion rather than the this depletion, because we have this positive bias already due to this positive charges that are lying inside the oxide. So it means that this statement S1 was false, but the statement is true, because it will result in the depletion region being formed earlier. So instead of this CV curve like this, we will be having CV curve something which will start over here. Okay, this would be for the low frequency, this would be for the high frequency. Okay, the CV will start first this from this curve, so it would be like this, it would be like this. There will be this difference in these two CVs, and this CV, this first CV is when there is no oxide charge, no oxide positive charge, and this case is when we have positive oxide charge. As simple as that. So this thing over here says that this S1 is false and S2 is true. Now, if I have to apply some, what I can say, we have seen that till now we had assumed that there is no charge in the oxide. As a result of this thing, we had said that the flat band voltage would simply be equal to the difference of the metal work function and the semiconductor work function. But if I consider now this phi m to be equal to, let me consider another case when phi m this phi m is equal to phi s, let us say. Okay, and as a result of this thing, phi ms is 0, and this flat band voltage, as for the specific case, clearly over here, since the bands are not flat even when we are applying zero bias, because this condition, this positive charges will result in the this depletion of these holes near the interface. So even when there is no bias, I will be having depletion of the carriers at the interface. Now, in order to encounter, or in order to have the flat band condition in this semiconductor, we need to apply some bias. So if I ask you people, what should be the bias? Should it be positive or should it be negative? What do you suggest? Should I apply negative bias at the gate to what we can say to encounter for the changes that have been occurring and due to this positive oxide charge, or should I apply negative charge in order to make the bands flat? So since I am getting no response, I assume that I have to answer it myself. So it since the gate bias we will be requiring, it should be opposite to that of the charge that is being uh, present in the oxide. So if the oxide is having positive charge, we need to balance this positive charge by applying some negative bias. So simply if we want to make the semiconductor bands flat, we need to apply negative voltage to the gate. As a result of this thing, the Fermi level will on the metal side will move up, and there will be this no band bending now in the semiconductor side, but there will be this band bending in the oxide itself. So this basically this whole assumption is based on the this whole thing is based on one assumption, that all the oxide charge lies at the interface. Okay, we have to be careful about this thing. Okay, all the oxide charge lies at the interface. Now if I have to apply this flat band voltage, which would simply be, let me draw this negative bias. This is the negative bias that we are applying on the metal side, and this is the Fermi level of the metal. Okay, it would be separated from the Fermi level of the semiconductor. If this is the positive charge on the semiconductor, okay, sorry, is this the positive charge inside the oxide, it would be having band bending like this, because field is from positive to negative, and this will be the field in the oxide. Okay, so this resulted in the separation of the Fermi level of the semiconductor and the metal. This would be the semiconductor Fermi level, which is close to the valence band because it is p-type substrate. Okay, and the intrinsic Fermi level will remain as it is. This would be the conduction band edge. Okay, this would be the conduction band edge. So basically, in order to accommodate for this positive bias, a negative bias has been applied at the gate. This is our gate, this is our oxide, and this is our semiconductor. So we have applied a what I can say, we applied a negative bias in order to accommodate for this positive bias changes simply. Okay, this means that we have to apply this negative bias. This negative bias VFB should simply be equal to this oxide charge divided by this oxide capacitance, and it should be negative because the oxide charge is positive. So it is as simple as that. So for having this flat band voltage, simply if now I consider both the effects, like for example, if I consider both the effects of this metal work function difference and the oxide charges, let me write it on the another slide, that if I consider both the metal semiconductor work function work function difference and the oxide charge oxide charges, I will be requiring the flat band voltage, which would simply be equal to the difference of this metal semiconductor work function minus times this oxide charge by the this oxide capacitance. So this would be the amount of bias that I would be requiring for in order to have this metalwork function, sorry, in order to have this zero band bending inside the semiconductor. So this flat band voltage, that we write it down again, flat band voltage is nothing but gate it is a gate to body, what I can say, it is a gate to body voltage, gate to body voltage needed to create flat band condition inside the semiconductor. Okay, and it has two components. It has two components. One is this metal semiconductor work function difference. Okay, and second is this oxide charges. This oxide charges, and we have taken both the effects, and we have assumed that for this thing we have assumed this oxide charges these oxide charges lie at the silicon dioxide interface. So this is one assumption, because if this is spread over the whole oxide, we need to have the integral for that thing. So let's not go into that particular. Now we have been given another statement kind of a question, where it has been told that uh, basically let us first let us write down the some of these what we can say oxide charges that can be present in this what I can say mm, in this MOSCAP. This MOSCAP can have four type of oxide charges. Let me let me write down those. Just we will write down the names, and you, if you are interested, you can look into that. So this basically this oxide charges will have four components. One will be this interface trap charge, another will be oxide fixed charge, another will be oxide trap charge, and another will be mobile charges. Okay, this is the mobile charges. So this is interface trap charge, this is the oxide fixed charge, this is the oxide trap charge, this is the mobile charge. Okay, these are the four components of this oxide charge. Now let's move towards this statement problem, which says that we have to consider the following statements about the MOSFET. For a MOS capacitor with gate voltage equal to threshold voltage. Okay, we are having some gate voltage which is equal to the threshold voltage. Which of the following statements are false? Okay, so the surface potential is equal to twice the what I can say, it has been twice the value of phi f. Okay. Second statement is there is no band bending in the semiconductor. Third statement is this inverter charge concentration at the interface matches the majority carrier concentration in the bulk. Okay. Fourth statement is surface potential is equal to phi f. Now we know that at this threshold condition, this gate voltage, we take the surface potential to be pinned at 2 phi f. Okay, the surface potential is pinned at 2 phi f. So this statement is correct. It says that there is no band bending in the semiconductor, which is false. No band bending only occurs at flat band condition. Flat band condition that we have seen previously. This was the flat band condition and this was the flat band condition and flat band bias for us, which was equal to the phi ms, the metal work function difference, and the oxide charge, the oxide, what we can say, the field inside the oxide that was present, it was equal to that thing only. So this statement is false. The inversion charge concentration at the interface matches the majority carrier concentration in the bulk. This is the correct statement. We had seen previously that at the interface, the majority carriers, now this the majority carrier concentration, which was earlier, for example, if we considered the Na, the acceptor concentration to be equal to some number A, now when we have this threshold condition, when we have this surface potential pinned at 2 phi f, we will be having the electronic concentration to be equal to the same value of the doping concentration or the acceptor concentration that we had used, because it is the definition of the inversion. The surface has to be as much, for example, as much electronic as it is in the bulk. So the charge, inversion charge, should have the electron concentration of the approximate equality to that of the bulk concentration of the holes. So this is correct statement. The surface potential is phi f. If we see that the surface potential has to be 2 phi f. So this is also false. So the false statements in this problem are 2 and 4. The false statements in this problem are 2 and 4. Okay. So option C is the correct option to go with. So basically this surface potential, if we consider this surface potential is nothing but, if I write down this surface potential again, surface potential is nothing but, it is simply the difference of the Fermi level, intrinsic Fermi level in the bulk minus the difference of the intrinsic Fermi level at the interface or at the surface, okay, divided by the q, which is the electronic charge, since this E is energy. So this is simply this what I can say, this surface potential definition. Okay, this is simple surface potential definition. uh, and this we know this, in this accumulation, this intrinsic Fermi level will move away, and it will go to the, for example, it will go to this, it will be more what I can say, whole dominated region. So when this would imply this this when, for example, when uh, uh, in accumulation, when I am in accumulation simply, EI at interface moves away and goes to top. Okay, which means that surface concentration of holes is greater than bulk. Okay, if surface concentration, if this is more than this value, it would mean that the surface potential is negative. Okay, in accumulation, so in accumulation psi s is negative. Oh, similarly for this depletion region, this intrinsic Fermi level will move towards this Fermi of the semiconductor, which means the surface will be more becoming more of n type, and as a result of this thing, this psi s will be positive. So basically, I have conditions on this psi s. This or right now, let me write it like this: conditions on psi s that will tell us about the mode of operation. If the psi s is less than 0, I will be having accumulation. Okay. If the psi s is equal to 0, which means that I will be having flat band condition. Okay, flat band condition. As you can see, this EI bulb and EI interface both are same in case of flat band. So I will be having this flat band condition. Now for the psi s to be less than phi f but greater than 0, I will be having depletion condition. Okay, now there is this phi f less than psi s, less than 2 phi f. This is weak inversion, condition. And between this phi f and psi s less than this this 2 phi f, 2 phi f plus n times Vt, this is the moderate inversion. And after this greater than psi s greater than 2 phi f plus n Vt, we have strong inversion. But you must have seen uh, till now we were saying that this 2 5 is the pinning point of the surface potential, and after this we will be having the strong inversion region. But you clearly over here you have seen this something, this n, we have this 2 5 plus some number n Vt, where Vt is this thermal voltage. We know it is 26 millivolts at 300 Kelvin approximately. Okay, so this n is known by the name of Swedish. It is known as the, this n is the Swedish factor. Okay, it is the Swedish. Okay, it is the Swedish factor, and it is generally between, this n is between 4 to 6. This is having the integer value. Not, I wouldn't say integer. It is having the value between 4 to 6. So for our operation, we mostly will say the strong inversion will occur at 2 phi. However, in the reality, the strong inversion occurs at some value 2 phi f plus n times Vt, where this Vt is the simply the thermal voltage. So it means that we will be having, let's say, 150 what I guess 150 millivolt in a shift in this surface potential in order to have this strong inversion region. So these are the this some regions, some conditions on the psi s surface potential in order to uh, validate our regions of operation. So if this psi s is negative, we have defined it psi s in the previous slide to be equal to the EI bulk minus the EI interface. So if this psi s is negative, for this case, we will be having accumulation. If this psi s is equal to 0, we will be having flat band condition when there will be no band, we can say no band bending. Okay, so at this between this phi f psi s greater than 0 and less than phi f, we will be having depletion, and we will be having the depletion of the holes, and as a result of which the electrons will be building up at the interface, and after that between the phi f to 2 phi f we will be having weak inversion. And there is some another region which might not be that much useful till to you people till this level, but when you go to the further advanced studies you will see that this also has some significance, this moderate inversion region, because this moderate inversion region there is transition going on from this weak inversion to the strong inversion. So whenever you have to model the regions from the weak inversion to strong inversion, there will be this moderate inversion region that need to be incorporated carefully. So this is all about this thing, this accumulation, or and this what I can say, the surface potential, the accumulation condition, depletion, and weak inversion conditions. Okay, so let's move towards another problem. Uh, uh, Moving towards this problem, first uh, let us rather say that uh, from this we have to surface charge density. Okay, if this is the surface charge density, then this requires this Poisson equation to be solved explicitly. But let me first build another concept which I had told you previously, that whenever I am applying some this bias on this MOS cap, this for example I am applying some bias on this MOS cap. This is the metal side, this is the oxide, this is the semiconductor. So wait a second, let me draw it clearly. Okay, so if I am applying some bias, gate to body bias VGB, so there will be this potential drop. Okay, let me draw this potential drop, since I am applying it on the metal side, I would rather have this VGB which is applied to this metal, and I will be having the drop in the oxide which would be simply denoted by psi ox. Okay, and I will be having some, sorry, it has, I will be having some drop inside the semiconductor. Okay, it would be denoted by this psi s, which is the surface potential, and and there will be this metal work function difference. Okay, this is the this potential drop uh, uh, whenever I am applying some bias. So VGB is simply equal to this psi ox plus psi s plus phi ms. Okay, this is the potential balance, rather I would say. This is potential balance that we are doing over here. So this is DC potential balance. Okay. Now, if there is some increment to this, for example, I am changing the potential, this delta VGB. So this increment will happen to this delta VGB, and there will be this increment in or decrement in this oxide plus delta psi s. But this there will be no charge change, there will be no change in the ions, because the increment is happening to the semiconductor and the oxide itself. So if now we draw the or if we now see the charges that are lying inside this material, the charge balance, overall charge has to be, in order to maintain the charge neutrality, we should have the positive charges and negative charges summing up to zero. If this is the gate charge, this has to be gate charge per unit area plus oxide charge per unit area plus semiconductor charge per unit area. This has to be equal to 0. The semiconductor charge is simply summation of two charges. One is the depletion charge, okay, and another is the inversion charge, okay. So this is the depletion charge, this QS, this is the depletion charge, and this is the inversion charge. So I am having two charges in the semiconductor, which is the which you can say this depletion charge and the inversion charge. Now, any increment or any change to this charge balance, this would simply be equal to delta QG dash. There will be no charge in this oxide charge because it's fixed kind of a thing. So we cannot change this oxide charge concentration by changing the gate bias. So if I am changing this gate bias delta QG, I will be changing this depletion charge and I will be changing this inversion charge per unit area. So this is the incremental charge balance. So this is the incremental incremental charge balance equation. Now, if we are required to find the semiconductor charge, it is at what I can say, it requires the solution to the Poisson equation. Since this problem is related to the surface charge density, this requires us to solve this Poisson equation in order to get the semiconductor charge. So since let's not go into the derivation itself, because I guess you might have seen this. So I would directly write down this semiconductor charge. Sorry, what is happening? Okay, I guess it is loading something. Okay, let's not worry about this thing. So this semiconductor charge is simply, it is given by this expression. Let me remind you, please do not get what I can say confused, or do not get carried away with this thing. So this magnitude of this QS is simply given by 2Q epsilon S and A, which is under the square root, and this whole thing is multiplied by, let me write it, Vt exponential of minus psi s by Vt. Vt is the thermal voltage, okay, plus psi s, oh sorry, it should be psi s plus psi s minus Vt, and this whole thing multiplied by exponential of minus 2 phi f pi Vt into Vt exponential of psi s by Vt minus psi s minus Vt. Let us not confuse ourselves with these brackets, and this whole thing is raised power by 1 by 2. Okay, this whole thing is raised power by 1 by 2. Now simply for the psi s equal to 0, there has to be no charge. Qs dash has to be equal to 0, which is the flat band condition. So now let us consider the case when psi s is negative. When psi s is negative, we are in we are in okay we are in accumulation. We are in accumulation. So we can, if psi s is negative, exponential of negative number, we can neglect this thing. Okay, we can neglect this thing, and we can assume that, let us assume that since psi s is negative and psi s is, what I can say, its magnitude is greater than, magnitude of psi s is greater than 4 times Vt. So it simply means, since I have neglected this thing also will be neglected, and this Qs in this, what I can say, in accumulation, in accumulation, in accumulation would simply be the function of this exponential of minus psi s by 2 phi t. So this is simply, it would simply be function of this accumulation charge would simply be function of exponential of, if I consider the magnitude, it would be psi s by 2 Vt. Okay, so this accumulation charge is proportional to the exponential of the surface potential. Okay, exponential of the surface potential. Now in depletion region, we can say, clearly say that this, or rather, going into the depletion region, let us go into the, rather into the, what I can say, the inversion region. This inversion region is psi s is positive, and it is, let us assume it to be much greater than 4 Vt. So in this thing, in strong inversion, psi s is positive, and thus exponential of minus psi s by Vt can be neglected, easily. So it would rather become this expression for this, assuming this psi s greater than 4 Vt as well, and as a result of this thing, this expression for the semiconductor charge in the, in this, what I can say, in the depletion and the inversion would simply become minus 2q epsilon s n a times, let us check, times Vt, Vt, Vt and this whole thing exponential of, okay, it would be exponential of Vt exponential of psi s minus 2 phi f by Vt thermal voltage plus psi s raised to power 1 by 2. Okay, this is in, this is the qs value in depletion and inversion, considering psi s greater than 4 Vt. It is 4, it's not 5. It is 4 Vt. Okay, so this is the expression for this. Now if this in what I can say, in depletion region, we can safely neglect this thing, and this qs will be proportional to the root of psi s in depletion. Okay, it will be proportional to the root of psi s, and this qs would be proportional to the exponential of psi s by it is 2, I guess. Let me check again. uh, Let me check again. Okay, so it is, wait a second, it is Vt itself. So it will be exponential of psi s by 2 Vt. It will be proportional to this 2 Vt. Okay, considering the square root. So it would be 2 Vt. This Qs in inversion. So basically, this graph, which you have seen in the lectures itself, it 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 simply says that this surface charge density, it depends upon the exponential of the surface potential in accumulation. It depends on the exponential of psi s. However, in this what I can say, in depletion region over here, sorry, in depletion region over here, it is proportional to the root of psi s, whereas in strong inversion it is proportional again to the exponential of psi s by phi t. So if we consider the statements that are given to us, it says that for a NMOS capacitor under strong inversion, the surface charge density decreases exponentially as a function of, in strong inversion. Let's be aware of this term, the strong inversion. So decreases exponentially as a function of surface potential, which is wrong. Increases exponentially as a function of surface potential, this is correct. Increases linearly, which is cross. Does not change, which is absolutely ridiculous. So option B is the correct option to go with. So we have seen how this charge, this surface charge density or the semiconductor charge, changes with the surface potential. It has this exponential dependence in the accumulation region. In the depletion region, it has the square root dependence on the surface potential. And in the strong inversion region, it has the again this exponential exponential dependence. Now, uh, till now, if you have any question, you can unmute and ask. Meanwhile, I will drink some water. If you have any question, you can unmute. Yes, Mr. Krishna Paul, you can ask. Yeah, yeah, you have raised your hand. Yes, Mr. Krishna Paul. Okay. If you have no question, yes, yes. There is no question. So let me proceed further. So let me proceed further in this. Let me uh, show you how we can obtain the inversion charge from this charge sheet approximation. Yes, I think some of you have unmuted yourself. You can speak if you have to ask something. Yes, Miss Monica. Again, if uh, so, let me continue. Basically, you people are having no questions. So let us consider that everything is fine, and let us move further in this. Now we have found out this expression for this charge, this surface charge in the what I can say in the depletion and the inversion region. Now, if I want to calculate the inversion charge, simply uh, I need to have this inversion charge per unit area. It would be simply equal to minus q, which is the electronic charge, plus, for example, this xc, which is the inversion charge width, and this n of x, which is the inversion charge, integrated over dx. But this whole thing will need numerical analysis. This will need numerical analysis, and it would be really cumbersome for us to solve this thing. So we resort to some important approximation, which is this. We resort to charge sheet approximation. Charge sheet approximation. This charge sheet approximation, it tells us it tells us that we can assume this inversion charge width, this inversion charge thickness, this xc, which is this inversion charge thickness, we can assume this thickness tends to 0. If this thickness tends to 0, so this there will be no potential drop considering this Gauss law. So there will be no potential drop across this layer, since its thickness tends, it is very thick, and we can consider this entire surface potential. We can consider we can consider that the entire surface potential psi s drops across the depletion rate. Sorry, is depletion rate. Yes, I guess I have to mute you people again. Okay, across the depletion with dB. Okay, so it means that this whole surface potential has been considered to be dropped across this depletion width, and this will help us to simplify the mathematics easily. So this inversion charge, which is basically for this kind of a MOS cap substrate, consists of these electrons, and it takes up the negligible volume. We have considered this assumption because of this very thinness of this inversion charge as compared to this depletion width. So as compared to this depletion width, we assume that whole surface potential will drop across this depletion width instead of this inversion layer. So this depletion width, let me write it with our conventional term x depletion. So this x depletion is simply now 2 times epsilon s psi s by qna square. Okay, so clearly from this, clearly the depletion charge is per unit area is simply q depletion is simply minus q times na into the depletion width. So it is simply minus 2q. So let me write it explicitly, minus 2q epsilon s na psi s square. So this is the depletion charge which we have obtained by considering this charge sheet approximation. Now sorry, this inversion charge per unit area plus this depletion charge is the semiconductor charge, because semiconductor charge is simply the summation of these two things. So inversion charge is simply equal to the difference of this semiconductor charge minus the inversion, sorry, minus the depletion charge. So this is as simple as that. So from this charge sheet approximation, we have obtained this Q inversion to be equal to minus 2Q epsilon S and A. This whole thing, this thing is psi S plus Vt. This is psi S plus Vt exponential of psi S minus 2 phi f. We have considered this 2 phi f to be the pinning point of the surface potential minus root psi s. Okay, this is the inversion charge from the charge sheet approximation. Okay, this is the inversion charge expression that we have obtained. Now let's move towards another problem. This whole thing generated, or this whole thing was taught in order to obtain this curve that we are seeing, this relation over here that you are seeing, how this surface potential determines this charge, semiconductor charge density profile. So this is whole thing that we have studied till now. Now again moving to our numerical problems. It says that we have to calculate the threshold voltage for the case, sorry, so for the case which is given to us. Okay, It says that we have to consider a MOS capacitor with p-type silicon substrate at some temperature which is equal to 300 Kelvin, and it is doped to a concentration of 10 to the power of 14 per centimeter cube. The oxide thickness is 50 nanometers, okay, and the phi ms, the metal work function, is minus 0.83, with this intrinsic carrier concentration to be equal to 1.5 into 10 raised power. Now we have seen this threshold voltage. If we consider this MOSFET to be free of these oxide charges, devoid of these oxide charges, we can simply say this threshold voltage is simply equal to phi ms plus 2 phi f, which is the pinning surface potential, plus the depletion charge divided by the oxide capacitance, which is associated with this material. So this depletion charge is simply Q times Na into XD, and in order to find this XD maximum depletion width, we can simply say this is pinned at surface potential of 2 phi f, 2 q 2 epsilon s, phi psi s is 2 phi f by q n a. This is simply equal to this is the maximum depletion rate. Okay, now this phi f is simply Vt ln of, please mute yourself, thank you, ln of Na by Ni. Okay, this is the phi f, so it means that 25.9 into 10 to the power of minus 3 ln of Na is given to be equal to 10 to the power of 14 over here, 10 to the power of 14 divided by Ni. Ni is 1.5 into 10 to the power of 10, 1.5 into 10 to the power of. So basically let us calculate this thing. So it is simply 10 divided by 1.5 into 10 to the power of 3 ln of 666.666 ln of into 25.9, which comes out to be equal to this phi f value 0.228 volts. Okay, so the depletion width, this depletion width maximum, will be 2 times epsilon s is 11.7 into 8.85 into 10 raised power minus 14 into 2 phi f. 2 into phi f came out to be equal to 0.228 divided by q times Na. Q is 1.6 into 10 raised power minus 19. Na is 10 to the power of 14. Okay, let us solve this. It's 2 into 11.7 into 8.85 into 2 into 0.228 divided by 1.6. If is 590.2 into 10 to the power of minus 10. Wait a second, some problem with the pencil. Okay, So now let's take its square root. 590.2, which is 24.29, 24.29 into 10 to the power of minus 5 centimeter. Now this Q depletion is simply 1.6 into 10 raised power minus 19 into Na is 10 raised power 14 into 24.29 into 10 raised power minus 5. So it would simply come out to be equal 10 raised to minus 24 into 10 raised to minus 10. So it is 24.29 into 1.6, which is 38.864. 38.864 into 10 to the power of minus 10 coulomb per centimeter square. Now for Vt, it is simply equal to 5 ms. 5 ms is having the value of minus 0.83. This is minus 0.83. It is minus 0.83 plus 2 times 5f. 5f is 0.228. 0.228 plus this 38.864 into 10 raised power minus 10. C ox is simply epsilon ox by T ox. Epsilon ox is 3.9 is the relative permittivity of the silicon dioxide into 8.85 into 10 raised power minus 14. T ox is simply T ox is given to us 50 nanometers. Okay, it is 50 into 10 raised power minus 9 meter or 10 raised power minus 7 centimeter. So basically it is 10 raised power minus 17, it is 10 raised power minus 3, so it is 10 raised power minus 3 above, and it is 38.864 into 50 divided by 3.9 divided by 8.85 divided by 10 raised power multiplied by 10 raised power minus 3. So it is 0.056. So it is simply plus 0.056. Okay, this is minus 0.83 minus 0.83 plus 2 into what I can say 0.228 uh, in brackets plus 0.056. So it is 0.32. So it is approximately equal to point this Vt is equal to approximately minus 0.32 volts. So let us check the options. Option A is the correct option to go. Now let's move towards another problem related to this MOSFET, which is which says that we have to consider this energy band diagram, which is given to us. Wait a second, let me have some water. So we have to consider this energy band diagram of this p-type semiconductor. Clearly this is a p-type semiconductor because the Fermi level, you can see this, let me zoom this Fermi level is closer to the valence band. Okay, so it is a p-type semiconductor. Okay. Now the band gap of this material is 1 electron volt. Okay, so the band gap of this material is 1 electron volt. So this whole thing is also 0.5 electron volts, or this small thing is equal to 0.3 electron volts. Okay, this difference between this intrinsic Fermi level and the Fermi level of the semiconductor is equal to 0.3 electron volts. Now uh, there's a, this states that a student was asked to fabricate a MOS using the below semiconductor such that it has the following parameters. The threshold voltage is given to us. It is given to be equal to minus 0.16. Okay. The oxide capacitance is given to us. It is 100 nanofarad per centimeter square. The metal work function is given to us to be equal to 3.87. The assumption over here is there is no charge within the oxide. So it means that the flat band voltage will be equal to the this metalwork semiconductor and metalwork function difference simply. This for the semiconductor work function psi s is simply equal to this chi. This is the chi. Okay, it is simply equal to chi plus EC minus EI. Yes, this thing, this EC minus EI plus EI minus EFS. Absolutely. Okay, because we know this total thing is the semiconductor work function. Okay, we know this thing. So now we have found out this EI minus EFS. It is equal to 0.3 electron volts, and this thing chi is equal to 4 electron volts. EC minus EI is equal to 0.5 electron volts. So overall this psi s is equal to 4.8 electron volts. This is the value of this psi s. Okay. Now for this threshold voltage, this threshold voltage is equal to Vt is equal to Vfp plus psi s. Psi s is the surface potential, which is equal to 2 phi f. Simply psi s equal to 2 phi f for considering the threshold condition. Okay, plus Q depletion by Cox. Okay, by Cox. Simply, since we are required to find the magnitude of this depletion charge per unit area, we will say simply this VFB is now equal to, since this is there are no charges inside the oxide, so VFB is simply equal to phi ms. We have seen this. We solved the previously when we had this oxide charge, and we said that VFB will just be phi ms minus the Q or this oxide charge per unit area divided by the oxide capacitance per unit area. But since we are having no oxide charge, the flat band voltage will simply be equal to phi ms. So this phi ms, sorry, what's happening with this thing? Okay, so the phi ms is simply equal to phi m minus phi s. Phi m is, sorry, so phi m is 3.87 electron volts. 3.87 electron volts. Psi s is 4.8. So it is simply equal to minus 0.9 electron volts. This is the semiconductor metal work function difference, metal semiconductor work function difference. Now this psi s, it shouldn't be like this, it should be psi s. This psi s is 2 phi f. 2 phi f is simply equal to, phi f is the clearly phi f is equal to this, it is equal to point this phi f has to be equal to, in order to be equal to phi f, we know it is this difference, simply this difference is the phi f. If this band bending has to occur, it has to be equal to 0.3 electron volts. So this 2 phi f is simply equal to now 0.6 electron volts. So Vt itself is minus 0.16. So if we put all these values in this equation 1, so it would be minus 0.16 plus VFB. So it is, sorry, equal to VFB. VFB is minus 0.93 plus 2 phi f is 0.6 plus Q depletion. Cox is simply, it has been given to us, it is 100 nanofarad per centimeter square. So it is 100 nanofarad per, which is 10 raised to minus 7 simply. Okay, let's calculate this value. It would simply be 0.93 minus 0.6 minus 0.16, which is 0.17 into 10 raised to minus 7. So this Q depletion is simply equal to 0.17 into 10 to the power of minus 7. It's the magnitude of this depletion charge. Or simply, it is equal to 1.7 into 10 raised to minus 8 coulomb per centimeter square. So let's check the options. So coulomb per centimeter square unit is correct, and also 10 to the power minus 8 is correct, but none of the options is matching, so we will go with none of these. So it is basically 1.7, so we will go with the none of these options. Now it says that with reference to previous question, what is the value of phi ms? We found out this value of phi ms previously. It came out to be equal to minus 0.93. So let's check the options. Yes, it's minus 0.93. Option B is the correct option to go with. Now let's move towards another problem, which says that we have to consider an ideal MOSFET which has the following parameters. The semiconductor is p-type, the oxide capacitance is 1.7 microfarad per centimeter square, and this MOSFET is under strong inversion. Okay, it is under strong inversion, and if this inversion charge density is what I can say is at 2 volt is equal to 2.2 microcoulomb. What is the inverse charge density at 4 microcoulomb? Now this is interesting problem, but since we have not gone into that depth for this inversion charge, but still I can give you insights of this, how this inversion charge changes with this what I can say with this uh, gate voltage, with gate to body bias. So if I write down the expression for this uh, gate to body, or what I can say, this capacitance in terms of gate to body bias, it would be simply let me write down the this gate to body bias, what I can say, condition first. So this VGB is equal to VFB plus psi s plus gamma root psi s plus Vt exponential of psi s minus 2 phi f by Vt. This is the condition on the, this is the relation between this surface potential and the gate to body bias. We can derive it, but it would take some time for me to derive it in here. You can try yourselves, and you will be amazed to get the results for this thing, and you will be really admired to see how you can use the potential balances that we have used till now and the charge balances to simply get this expression. You simply will use the expression for the VGB equal to phi ms plus psi s plus psi ox. That is the potential balance equation. You will simply use that thing to derive this equation that you are writing over here. So this gamma is the body coefficient. You have seen this in the lectures. This body coefficient is given by this 2q epsilon s Na, which is under the square root divided by this oxide capacitance per unit area. This is the body coefficient that you know. If you draw this psi s versus VGB, you will see that it will pin to a particular value of psi s after some value. So let's not go into that detail, but let us just sorry, but let us just try to see the inversion charge in terms of this psi s and the VGB itself. So if I write down that expression, it is simply equal to this expression is simply equal to Q inversion is simply equal to minus C oxide per unit area VGB minus VFB minus psi s minus gamma root psi s. Okay, this is the relation for the inversion charge in terms of the gate to body bias, and the surface potential. So if sorry, wait a second. So if now I try to manipulate this equation, or if now I try to relate it with this interpolate this equation, I would see that this equation can simply be written as some VGB. This inversion equation can simply be written to be equal to minus C ox prime VGB minus VTO. Okay, this VTO is, if I draw that inversion charge, this inversion charge that I have written previously, this inversion charge with this gate bias, gate to body bias, it would simply be looking like this thing. Okay, so if I try to interpolate this exponential, this is this magnitude, it is in coulomb per centimeter square, and if I try to interpolate it on this x-axis, it would be some value which would be denoted by VTO. Okay, it would be a linear line. This whole thing, this whole region is the strong inversion region. Okay, it is the strong inversion region. So I can simply say or interpolate this whole expression by writing this VGB minus VTO. This is the interpolated, or this is also known by the definition of the classical threshold voltage. Okay, so this VTO is the threshold voltage. Okay, so I can simply say that this Q inversion is simply equal to, if I consider its magnitude only, so it is C ox prime Vg minus Vto. Now if I use this expression and try to find the inversion charge density under the assumption of strong inversion, remember we are in strong inversion. Okay, so we are in strong inversion, and it means that this inversion expression is C ox times Vg minus Vto. Now considering the first condition, when I am at Vg bias of 2 volt, the charge, inversion charge is 2.2 microcoulomb per centimeter square, and the oxide capacitance is 1.7 microfarad. So it means that I am at 2.2 microcoulomb times the oxide capacitance, which is 1.7 micro. This is 1.7 micro into Vg. Vg was 2 minus VTO. Okay, let me solve this. This will go with this thing, and I will be simply left with VTO, and this thing will be 2.2 divided by 1.7. 2.2 divided by 1.7 minus 2, it would be 0.706 volt. Okay, now at Vg equal to 4 volt, Q inversion is simply now 1.7 into 10 raised to power minus 6. Okay, now Vg is 4 and VTO is minus 0.706. We found out this VTO previously, so plus 4 into 1.7, which is approximately equal to 5.6 microcoulomb per centimeter square. So let's check the options. Option A seems to be the correct option, so we will select option A for this problem. So I guess this is it on the from my side for considering the problem solution part. Now, if you have any specific queries, I am happy to answer those. Please unmute yourself if you have any question, so that we can try to answer those questions. Okay, I am waiting for your responses. So I guess we have no questions. I guess we have no questions. Let me check the chat box. Okay, there is no question in the chat box as well. So I assume that we have no questions. Let us end today's session. I, I, I thank you all people for joining today's session. So thank you.